What if I told you that everything you think you know about gravity, the force that keeps your feet on the ground and planets in orbit, was proven incomplete on one cloudy day in 1919? For centuries, Isaac Newton's laws were the bedrock of science, trusted to navigate ships and predict the motions of the heavens. But then came Albert Einstein with a revolutionary idea. Gravity isn't a force pulling on things. Instead, he claimed, it's the very fabric of space and time bending and warping around massive objects. It was a beautiful theory, but was it true? The scientific world was about to find out, and the reputation of classical physics hung in the balance, all depending on a few blurred photographs of distant stars taken during the fleeting moments of a total solar eclipse. In 1915, while Europe was engulfed in war, Einstein was in Berlin, quietly finishing his masterpiece, the theory of general relativity. His equations described gravity not as an invisible pull, but as the geometry of the universe itself. This idea wasn't just abstract. It made a daring, testable prediction. Einstein calculated that light from a distant star grazing past the sun should be bent by its immense gravity by exactly 1.75 arcseconds. That's a tiny angle, like seeing a single human hair from over 100 feet away. But here's the crucial part, a Newtonian calculation, where light has a kind of weight, but space stays flat, predicted a bend of only half that amount, 0.87 arcseconds, and some traditionalists still insisted light wouldn't bend at all. It was a three-way showdown: Einstein, Newton, or nothing. There were no fudge factors, no room for error. The universe itself would deliver the verdict. Across the English Channel, a British astronomer named Arthur Eddington, one of the few who truly understood Einstein's dense mathematics, saw an opportunity. Eddington, a pacifist, believed a joint scientific effort could help heal the wounds of war. He and the astronomer royal Frank Dyson planned 2 expeditions to observe the total solar eclipse of May 29, 1919. One team would travel to Sobral, Brazil, and Eddington himself would lead another to the small island of Príncipe off the coast of West Africa. The plan was simple in concept, but incredibly difficult in practice. Photograph the stars visible near the sun during the total eclipse. Then compare those photos to reference images of the same stars taken when the sun was in a different part of the sky. If Einstein was right, the stars in the eclipse photos would appear to have shifted slightly outward, their light forced to curve around the sun's warped spacetime. The 1919 eclipse was perfect for the job, passing in front of a bright cluster of stars. But as the day dawned on Príncipe, Eddington's heart sank. Heavy clouds and rain choked the sky. In Sobral, the other team battled blistering heat that threatened to warp their delicate telescope mirrors. After years of planning and a journey across the ocean, the most important experiment of the century was at the mercy of the weather. As totality began, the moon blotted out the sun, revealing its ghostly corona. For a few precious minutes, the world held its breath. Then, a miracle. Through fleeting breaks in the clouds, Eddington frantically exposed his photographic plates, capturing just 16 images. He had no idea if the faint specks of starlight he caught would be clear enough to measure it. The fate of physics was now sealed on a few fragile sheets of glass. Back in England, the painstaking analysis began. For weeks, Eddington and Dyson hunched over the photographic plates with micrometers, meticulously measuring the positions of the stars. The results started to emerge. The plates from Eddington's expedition on Príncipe, despite the clouds, pointed towards Einstein's value. The main telescope at Sobril confirmed it. There was one other set of data from a backup telescope in Sobril whose images were badly blurred by the heat. It leaned closer to the Newtonian value, but was clearly compromised. The evidence was in. On November 6, 1919, at a historic meeting of the Royal Society in London, the verdict was announced. The bending of starlight matched Einstein's prediction. The next day, newspaper headlines exploded across the globe. Revolution in science. Lights all askew in the heavens. Almost overnight, Albert Einstein was transformed from a respected but obscure physicist into the world's first scientific superstar. His iconic image became synonymous with genius. The Eclipse experiment did more than just confirm a theory. It gave the world a powerful story of a new, weirder, more wonderful reality. While few understood the math, everyone could grasp the image of starlight bending as it passed the sun. Of course, there were controversies. Some critics later argued that Eddington might have been too eager to prove Einstein right, pointing to the discarded data. But history has been the ultimate judge. Over the next century, every new, more precise measurement from radio telescopes to space-based observatories has reconfirmed the result. General relativity is no longer a radical theory. It's the foundation of modern cosmology, essential for everything from understanding black holes to making your GPS work accurately. Newton wasn't wrong, just incomplete. His laws were a brilliant chapter in the story of science, but Einstein had written the next one. The 1919 eclipse was the moment humanity saw that the universe wasn't a rigid, predictable machine, but a dynamic, curving, and magnificent tapestry. Thanks for watching, and if you enjoyed this journey through scientific history, be sure to subscribe for more.